Okay, so um, okay, so we're in business now. So going back to the PowerPoint. So the next law we're going to talk about is what is called the law of combining volumes. And this deals with a situation where you're having a chemical reaction. And it's a reaction which involves gases, all right? And basically what we'll be doing pretty much for a good part of the rest of the chapter is what we call gas stoichiometry, right? We all know what stoichiometry is already from before. Stoichiometry is basically looking at quantitative relationships between substances involved in a reaction. In this particular case, we'll be looking at gaseous reactions or reactions involving gases. So this law says that when gases are measured at the same temperature and pressure and they're allowed to react, the volumes of the gas reactants and products are in small whole number ratios, all right? And what you're going to see here is that the ratios that we're talking about here pretty much mirrors the mole ratios, right? If the temperature and pressure of all the gases involved in the reaction are the same, then basically the volume ratios will be the same as the mole ratios. So for example, it says here, at a given temperature and pressure, 2 liters of hydrogen will react with 1.00 liters of oxygen. So the question is, why is it there's a 2-to-1 ratio? Well, if you look at the equation, which I'm quite sure you're all familiar with, the reaction between, okay, hold on. Okay, so the reaction between hydrogen and oxygen to form water. And if you were to balance it, you'll see that there's going to be a 2-to-1 mole ratio between the hydrogen and the oxygen, all right? So what this law is predicting is that the volume ratios is going to be the same, right? And it doesn't matter what the volume units are. Basically, the volume ratio between the hydrogen and oxygen would be that 2 volume units of hydrogen will react with 1 volume unit of oxygen to form 2 volume units of water. And now we're assuming, of course, that these are all gases, right? So basically, that's what this law is saying. Basically, what it's saying is that the mole ratios will be the same as the volume ratios. But there's a caveat, and that is that the temperatures and the pressures of all the gases will be the same. All right. Once you have that constraint, then basically we can use the mole ratios to be the same as the volume ratios for these reactions involving gases. And I think there's another example I have here, right? The reaction between nitrogen and hydrogen. Let me get rid of these writings here so you can all see. Okay, so this says, here's the other example. At a given temperature and pressure, 6.00 liters of hydrogen will react with 2.00 liters of nitrogen to form 4.00 liters of ammonia. So why is it that we have this ratio, 6:2:4? And you'll notice, of course, by simple arithmetic, that this ratio is the same thing as, 3:1:2, right? And again, if you go to the balance equation for the reaction, nitrogen plus hydrogen to form ammonia. And to balance this, we're going to need 2 of these here, and we're going to need 3 of these here, right? So again, you're going to see the ratio, the mole ratio being the same as the volume ratio. So basically 1 volume unit of nitrogen will react with 3 volume units of hydrogen to form 2 volume units of ammonia. So that's where we get that ratio from, the volume ratios. Again, the constraint is that all the temperatures, well, the temperatures and pressures of all the gases will be the same, all right? So that makes life easier for us when we're doing calculations involving gases. But of course, we can encounter a situation where the temperature and pressure of all the gases are not the same. So therefore, that's a bit more complicated. And we're going to look into those examples. But before we do that, one more thing before we leave this page, let me get rid of that here, is that we don't even need to know what the temperatures and pressures are, as long as they're the same, right? As long as the temperature and pressures are the same for all the gases involved, then basically we can assume that the volume ratios would be the same as the mole ratios, all right? Okay, so just to give you a pictorial representation of the reaction that we just looked at, the reaction between nitrogen and hydrogen, let me rewrite the equation here again. It's nitrogen plus 3H2 to give 2NH3. That's the equation, right? So basically, at the same temperature and pressure as stated here, then in terms of the volume units, in terms of the volume units, oh no, this is not the reaction. I'm sorry, this is the reaction between hydrogen and oxygen. So let me erase this here, and let me rewrite the correct equation. So it's a reaction between hydrogen, 2 of these, plus oxygen to form 2 moles of H2O, all right? So this is a pictorial representation of that reaction. So basically, you have, assuming that all these flasks occupy the same volume, so basically we have 2 volume units of hydrogen reacting with 1 volume unit of oxygen, and the result will be 2 volume units of water, assuming that, of course, all the substances involved in this reaction are gases, all right? The volumes are the same, and the temperatures, well, the temperature and pressure are the same for each of these gases. And the reason why the volume ratios are such is because for the same temperature and pressure and volume, for the individual gases as indicated here, the number of molecules would be the same, all right? So as stated here, the volume ratios would be the same as the mole ratios based on the balance equation. All right, so based on what we have just learned, then we should be able to easily do this problem, which says how many liters of oxygen are consumed for every 10.0 liters of CO2 produced in the combustion of liquid pentane, and it gives you the formula if all the volumes are measured at STP. All right, so this is a typical gas stoichiometry type question. So what would be the very first step in solving this problem? What would be the very first step? Write a balance equation. Okay, so what would be the reactants based on the information provided here? What would be the reactants in this reaction? Oxygen is one of them. All right, very good. I'm sorry? CO2? No, because it says carbon dioxide is produced. So carbon dioxide would be a product, all right? But there's another reactant here based on the question information given in the question. What's the other reactant? C5H12, and it says that it's liquid pentane, so we're going to put L there. And what would be the other product of this reaction? H2O, because whenever you're burning any hydrocarbon, which is, this is a hydrocarbon, then the products will always be carbon dioxide and water. Then we have to balance the equation. So how would you go about balancing this equation? Let me make this a little bit more neater. Okay, so how would you go about balancing this equation? Well, a what? An 8? Sure about that? What else? Okay. A 6 for the H2O. Okay, yeah, that's correct. Okay, so this is the balance equation for the reaction. All right. So what's the next step? Now that you have the balance equation, now look at the numbers. The question is asking for how many liters of oxygen are produced or consumed, I'm sorry, for every 10.0 liters of carbon dioxide produced. All right. So basically you're given 10.0 liters of CO2, and the question is asking how many liters of oxygen. So let's start off with the 10.0 liters of CO2. And my question is, what would be the conversion factor you would use based on the balanced equation to convert from liters of carbon dioxide to liters of oxygen? You could do that, but that's not necessary. You could do that, but you're introducing, and you get the right answer, but you're making it longer. So there's an alternative way based on what we just discussed. Remember, we said that the volume ratios are the same as the mole ratios as long as all the gases are at the same temperature and pressure. So how would you express the volume ratio right here as a conversion factor? What would go up top here and what would go below here as a denominator? Right, the 8 would go up top, and more specifically, that would be 8 liters of oxygen. All right, and then what would go below here? 5 liters of CO2. So basically, that's the volume ratio, which is the same as the mole ratio. So basically, that's 8 times 10, 80. 5 into 80 goes what? I'm too lazy to do the arithmetic in my head. Oh, that's 16. Yeah, 16.0. So the answer is going to be 16.0, and that will be liters of oxygen. And that's it. All right, so that's a relatively simple problem. And as I said before, it's relatively simple because we're assuming that all the gases are at STP conditions, or fixed condition, fixed temperature and pressure. Okay, now we're going to get into situations where that's not the case, right? So basically, when it comes to solving stoichiometric type problems where the temperature or pressure of the gases may vary, then we have to basically use the ideal gas equation to help us to solve this problem. So as stated here, we can use the previous law that we discussed, basically for problems where all the gases are at the same temperature and pressure, but that's not always, of course, going to be the case. So what we have to do is use basically what we learned earlier concerning stoichiometry with what we learned in this chapter concerning the ideal gas equation, right? So if you remember, any stoichiometric problem that you're going to deal with comes down to this right here, where you convert the moles of one substance involved in the reaction into the moles of the other substance by multiplying by the appropriate conversion factor here. And of course, the conversion factor here, the mole ratio, comes from the mole ratio established in the balanced equation. Now, in the case of gases, there are other variables that can come into play based on the question that you're given. So for example, you could be given the pressure, volume, and temperature, and then using those values, you can use the ideal gas equation to find the number of moles of one gas. So let's say we use P, V, and T to find the moles of A, and then we use the conversion factor to find the moles of B, and then depending on how the question is worded, you could be asked to determine P, V, or T based on the information that's provided, all right? So that's an extra wrinkle that can come into play when it comes to solving gas stoichiometry type problems. So here is a good example of such a problem. So the question here talks about this reaction here, which is used, I'm not sure this is used anymore currently in airbags, but previously, this is the reaction that takes place when there's an accident. They have this mechanism here where the sodium azide, sodium azide is basically impacted and basically produces nitrogen, which fills out the airbag, all right? But I think they use something else instead nowadays. But anyway, so this is the balanced equation here for the reaction. And the question says here, what volume of nitrogen measured at 25 degrees Celsius and 0.980 atmospheres is produced by the decomposition of 62.5 grams of the sodium azide? So basically, you're starting off with 62.5 grams of sodium azide. And the question is asking for the volume of nitrogen. So I'm going to presume that the volume is expressed in in liters, and it says measured at 25 degrees. So I'm going to put at 25 degrees Celsius and the pressure being 0.980 atmospheres, all right? So this is basically what the question comes down to. So the first thing I would do is start off with the 62.5 grams of the sodium azide, and I will convert that to moles. So I'm going to have 1 mole of sodium azide above, and down here the molar mass. So being the lazy person I am, I'm going to cheat a bit and use my trusty old molar mass calculator to find the molar mass of sodium azide. So NaN3. Let's see what that gives. That gives 65.01. So that will go down here, 65.01 grams of sodium azide. Change the ink on this thing. Okay, so the next step now would be looking at the mole ratio between the nitrogen and the sodium azide. And we can see that's a 3:2 mole ratio. So the way we will represent that here is that I'm going to put 3 moles of nitrogen above as the numerator and 2 moles of sodium azide below as the denominator. And I'll work that out, right? So let's see what this gives. And again, please, folks, do this yourself so that if I'm wrong, I can be corrected. Times 3 divided by 2. Okay, so this is what I got. I got 1.44 moles of nitrogen, all right? And that would be the N in the ideal gas equation, which we're all familiar with. Remember, the ideal gas equation is PV is equal to nRT, right? Now, what the question is asking for is the volume. What the question is asking for is the volume. It's asking for V, right? So based on this equation here, we can say that V is equal to nRT over P. So basically, all we have to do is put the numbers in. We have the temperature, which, by the way, we have to convert to Kelvin. When we do that, you're going to end up with 298 Kelvin, all right? So that's the temperature, and we have the pressure. And we just calculated the N, the number of moles, right? So all we have to do from here is plug the numbers into this equation. So we're going to have, let me do this down here. So V will be equal to 1.44 moles times R, which is always 0.0821 liters atmospheres over mole Kelvin times the temperature, which is 298 Kelvin, all divided by P, which is 0.980 atmospheres. And then you see how the units cancel out. The atmospheres will cancel, the Kelvin will cancel, the moles will cancel. So the final unit here that you're going to be left with would be atmospheres. So let's see what that gives. 1.44 times 0.0821 times 298 divided by 0.980. And according to my calculation, the answer I got is rounded up to 35.9 liters. And that's how that is done. All right. Any questions about this one? Any questions? Any questions? Okay, moving along. So far, basically all the problems that we have been looking at dealt with gases by themselves, not mixed with other gases, all right? So now we're going to look at another law called Dalton's law of partial pressures, right? And this law is applicable to mixtures. And it's a very simple law. Basically, what this law says is that the total pressure of a gaseous mixture is equal to the sum of the partial pressures exerted by the separate gases in the mixture. Now, this term partial pressure basically represents or is referring to the pressure that the gas would exert if it were by itself in the container, right? So if you imagine a mixture of gases, for example, the air we breathe, right? The air we breathe is a mixture of gases, nitrogen being the major component. You have oxygen, and then you have some minor gases like carbon dioxide and helium and so on. So basically, when we talk about the partial pressure of each gas in a container, then basically what we're saying, what we're referring to is the pressure that the gas would exert in the container if the gas were by itself, all right? So that's basically what this law is saying. The total pressure of the gaseous mixture is the sum of the partial pressures. So this is a simple equation which describes this particular law. P total, which is the total pressure, is equal to the pressure of gas 1 plus the pressure of gas 2, and so on and so forth, all right? So as I said before, this is the partial pressure definition, the pressure that the gas would exert if it were by itself. And therefore, we can write down individual expressions for each of these gases in the mixture. So P1 would be, and this is based on the ideal gas equation in each case, right? So P1 is equal to the number of moles of that gas, N1, times RT over V. And then P2, you have a similar expression here, and P3, you have a similar expression. And taking this into account, this can lead us into something interesting. So what I'm going to do is get out of this here, and then I'm going to go to one of my writing applications here. Okay, so what we had before, what I just showed you is P total is equal to P1 plus P2 plus P3 all the way to Pn, all right? So if we remember, I said also that P is equal to nRT over V, right? So if we substitute this here for each of these gases into this expression, this is what we're going to end up with. We're going to end up with N1 RT over V plus N2 RT over V plus N3 RT over V. And of course, we continue to NN RT over V. And I should have mentioned, which should be obvious to you anyway, that for each of these gases, the temperature and volume would be the same because they're all in the same container, right? So that doesn't change. The only thing that will change for each gas would be the number of moles. So that's why we have these separately shown. Now, we can simplify this equation by factoring out the RT over V. When we do that, we're going to end up with N1 RT over V times N1 plus N2 plus N3 plus all the way to Nn, all right? So basically, all of this here represents the sum of the moles of all the gases in the mixture. So we can simply call that NT, right? The total number of moles of all the gases in the mixture. So therefore, that simplifies this equation. PT is equal to NT times RT over V, all right? So basically, all we have to do to find the total pressure of a gaseous mixture, if we know what the temperature is and we know what the volume is, then all we have to do is add all the moles of the gases, and that would be the NT right here. And then we plug that into this equation, and that gives us the total pressure of the gaseous mixture, all right? Okay, any questions about this? Any questions? Any questions? Any questions? Okay, going back to the PowerPoint here. Okay, so let's look at this example here. This question says, you have a 1 liter sample of dry air at 25 degrees, which contains, and it gives you the amounts in terms of moles of the different gases in the mixture. So the question is asking for you to calculate the total, the partial pressure of all the gases in the mixture and the total pressure of the gaseous mixture. So basically, to start off with, on color. Okay, so to start off with, remember now that P is equal to nRT over V. What the question is asking for us to do is to calculate the partial pressure of all the gases in the mixture. So we have to basically use this equation here and calculate the pressure of each gas. So I'm going to start off with the nitrogen. The partial pressure of nitrogen would be the number of moles of nitrogen, which they gave us here, which is 0.0319 moles, times R, which is 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is 25 degrees Celsius, which is the same thing as 298 Kelvin, sorry. And then divided by the volume. What's the volume? 1.00 liters. And we work that out, right? And pretty much it's the same calculation for all of them. In the case of oxygen, it's the same process. The only difference would be the number of moles. So in the case of oxygen, that's 0.00856 moles times 0.0821 liters atmospheres over mole Kelvin times 298 Kelvin. And we work that out. Oh, no, first we have to divide by 1.00 liters. How could I forget? And we work that out. And basically do the same thing for all the other gases. I don't think I need to show you how to do it for the rest of them. It's the same thing. The only difference between each of the calculations would be the number of moles. And then once you do that, once you solve that for each of them, then to get the total pressure, you just add them up according to Dalton's law. And that's it. That's how you'd solve that particular problem. All right. So I'm going to leave you to do the rest on your own. If you have any questions about that, which I don't think you should have any problems anyway, but just in case you encounter any difficulty, please feel free to contact me about that. All right. Okay. Any questions? Any questions? Any questions? Okay. This is just a pictorial representation of Dalton's law. So basically what we have here are two cylinders, one containing hydrogen and the other one containing helium, all right? So we're assuming that there's no reaction that will take place, and that is certainly true because helium is not reactive, all right? So in this cylinder here, we have 0.60 moles of hydrogen. The pressure is 2.9 atmospheres when the volume is 5.0 liters and the temperature is 20 degrees Celsius, right? In this cylinder here, same conditions in terms of volume and temperature, different amount of helium molecules present, 1.50 moles, and this is the pressure that's exerted. So if you mix these two gases in the same container where the volume and the temperature are the same, then basically the pressures are additive. In other words, the total pressure here, 10.1 atmosphere, is the result of adding the pressure of helium to the pressure of hydrogen. And the same is true for the moles, right? So basically that's what this is illustrating, the fact that basically for a mixture of gases, the sum of the pressure of all the gases in the mixture is equal to the total pressure of the mixture, all right? So here's a question being asked. The question says, what would be the total pressure if 0.90 mole of nitrogen were added to the gaseous mixture? So how would you answer that question? So you have this mixture already, right? And to that mixture, you're adding 0.90 moles of nitrogen. So how would you determine the total pressure of that resulting mixture? You could do it that way. So what he was suggesting is that you find the partial pressure of the nitrogen that you added. And that's one way of doing it. It's a bit longer, but that's one way of doing it. So basically what you would do is, based on what he's saying, is that find the partial pressure of N2, and that would be equal to 0.90 moles times R, which is 0.0821 liters atmospheres over mole Kelvin times the temperature. What's the temperature? 20 degrees, which is 293 Kelvin, 293 Kelvin, and then divide that by the total volume, which is 5.0 liters. Right, so once you find that out, whatever that gives, then you add it to the total pressure that was there before, right? So that's one way of doing it. Now for me, again, being the lazy person I am, an easier way would simply be add 0.9 moles to this total mixture here, which would give you 3.00 moles. And then I would use that in the equation that I showed you before. P total is equal to N total times RT over PV over P. What am I saying? Over V, my bad. All right. And this 3.00 moles would go right here. Right. And then I do the rest of the calculation, and that would give the same answer that you would have gotten if you use your method. All right. Okay, so that's basically how you would solve that particular problem in the question here. All right. Okay. Another thing I want to talk to you about before you continue with your assignment is this concept known as mole fraction. So mole fraction is basically another way of expressing a concentration of a component in a mixture. All right. We're going to apply it to gaseous mixtures, but literally can be applied to any mixture, even solutions, aqueous solutions, and so on. In fact, for those of you who plan to do Chem 2, you're going to see this mole fraction concept being applied to other solutions apart from gaseous mixtures. So what do we mean by this term mole fraction? As stated here, the mole fraction of a gas is a fraction of all the molecules in a mixture that are of a given type. And we can calculate it using that equation that you see there, right? So imagine you have a gaseous mixture and you want to calculate the mole fraction of gas 1 in the mixture, then this is the equation you would use. The mole fraction of gas 1 would be the number of moles of that gas divided by the total moles of all the gases in the mixture, right? And one key thing you need to recognize about this equation is that as a result of the fact that the units here is moles and the units here is moles, that means that these two will cancel out each other, which means that the mole fraction has no units. All right, so there's no units associated with the mole fraction because you have moles divided by moles. All right, and it's a fraction. Basically, what that tells you is that in any mixture, one component must have a mole fraction somewhere from 0, which means that there's none of it present, to 1, which means that it's 100%. All right, so the mole fraction value cannot go beyond either 0 or 1. It has to fall somewhere in between. All right, now, because there is a direct relationship between pressure and the number of moles of gas, provided that the temperature and volume are constant, then we can use pressure values for the gaseous mixtures to calculate the mole fraction of a component in that mixture. So this is another equation here that you can use to determine the mole fraction of a gas in a mixture. It's the pressure of gas 1 divided by the total pressure of the gaseous mixture. So you can use this equation or this equation to calculate the mole fraction. And if you're given a question where you're given a mole fraction and you're asked to find the pressure of one individual gas, again, assuming that you know the total pressure, then you can determine that by using this equation right here, all right? So that's basically an introduction to this concept of mole fraction. So let's see if we can apply that to this particular problem. This question says the main components of dry air by volume are, and it gives you the numbers for the different gases, nitrogen, oxygen, argon, and carbon dioxide. So the question is asking, what is the partial pressure of each gas in a sample of air at 1.00 atmospheres, all right? Well, that's pretty simple because basically we said that the partial pressure of a gas would be equal to the mole fraction of that gas times the total pressure of the gaseous mixture, right? We know what the total pressure is. It's 1.00 atmospheres. Now, these percentages, as it says here, are percentages by volume, but they can also represent percentages in terms of mole fraction, right? Because PV is equal to nRT, right? if the pressure is constant and the temperature is constant, then the number of moles will be proportional to the volume, right? So basically, we can use these numbers to represent the partial pressures. So we can do the calculation for gas, for the nitrogen gas. The partial pressure of nitrogen gas would be this number expressed as a fraction, which would be, or as a decimal number, which is 0.7808. And we multiply that by the total pressure, which is 1.000 atmospheres. And that's it. We're going to get 0.7808 atmospheres, right? And basically, we're going to do the same thing for oxygen and the other gases. In the case of oxygen, that would be 0.2095 multiplied by 1.00 atmospheres, and that gives you 0.2095 atmospheres. And basically, it's the same thing, same calculation for argon and for carbon dioxide, right? You simply multiply the fractions or the percentages by the total pressure, and that gives you the partial pressure. So again, I'm going to leave that for you guys to work on your own. Okay, one application of what we just learned concerning Dalton's law is that we can apply this to a situation where we're collecting gases over water. Now, there are some gases that can be conveniently collected over water after they're generated from a reaction, but that's not true for all gases. In particular, the gas would have to be very insoluble in water, right? So this method for collecting gases can be used for gases like oxygen, hydrocarbon gases like methane, ethane, and so on, all right? If the gas is very soluble in water, then this simply won't work, as you're going to see shortly. So basically, the way this particular apparatus is set up is that we have a trough with water in it, and then we invert in that trough a jar, which is also filled with water initially, right? And then we have a tube that is connected to the reaction vessel where the oxygen or the other gas, whatever gas is being produced, is generated. And that tube is led into the flask, right? So when the gas is produced, then the gas is led into the flask here. And because the gas is not soluble in water, it basically collects here above the water. And of course, it's going to exert some pressure on the water surface. So as more and more gas is being collected here, then basically the water level here will go down. And what we typically do in this sort of setup is that we basically collect enough gas such that the water level inside the jar is the same as the water level outside the jar. And the reason why we do it that way is because when we do it that way, we know that the gas that is collected here will have the same pressure as the barometric pressure that is exerted on the surface outside. Now, there's a very important question that is being asked here. The question says, what two gases are present here above the water? Remember, the gas that's being produced here is oxygen. So what would be the other gas? And the question is answered right here. The gas collected is usually saturated with water vapor. So not only do you have oxygen gas collected above the water inside the jar, you also have water vapor collected here as well. And that is true for most liquids. For most liquids, you're going to have a certain amount of vapor of that liquid above the surface of the liquid itself. So that is no less true for water. So therefore, what that means is that you have a gaseous mixture here. Two gases. One would be the gas that you're collecting, which in this case is oxygen, and the other gas would be the water vapor. So therefore, the total pressure exerted here, which is equal to the barometric pressure here, would be the pressure of both gases, right? So that's why we have this equation here. In fact, let me include an initial equation which should be here. And that is that P total, which is the total pressure of the gaseous mixture, would be equal to the pressure of the gas that is collected plus the vapor pressure exerted by the water gas that is collected as well, right? So basically, if you rearrange this equation, you're going to get this equation right here, where P gas is equal to the total pressure minus the vapor pressure of water. And as we said before, the total pressure that is exerted, the total pressure that is exerted here would be equal to the barometric pressure, right? So therefore, we can replace P total with the barometric pressure, and that will give us the pressure of the gas. So once we know these two values, we can determine what the pressure of the gas is that we're collecting. Now, the barometric pressure can be determined because we have an instrument known as a barometer, which can measure the barometric pressure, right? And as far as the water vapor pressure is concerned, there are tables that basically gives you different values of the water vapor pressure at various temperatures. So basically, you can refer to that table, and therefore you can put the numbers in, and that will give you the pressure of the gas when you plug those numbers into this equation, all right? So that's basically what is involved when it comes to pressure measurements of gases collected over water. Okay, so based on what we have just learned, oops, let's look at this example right here. In fact, what I'm going to do is copy and paste this so I can have it to refer to while we're solving this problem. So let me go to here. Let me clean this up. And then let me see if I can paste this here. Okay, what is going on here? Let me try this again. Oh, I think I know what happened. It's white. So let me make that black. And then let me copy this. And let me paste this here. Okay, now we're in business. All right, so this question says, hydrogen produced in the following reaction is collected over water at 22 degrees Celsius when the barometric pressure is 742 torr. It gives you the equation, balance equation, and the question is asking, what volume of the wet gas will be collected in the reaction of 1.5 grams of aluminum in excess hydrochloric acid? Okay, so the first thing I would do is, I would start off with the 1.50 grams of aluminum. And what I'll try to do is determine the number of moles of hydrogen. All right. Okay, so how will I do this? First thing I would do is convert the grams of aluminum to moles of aluminum. So you're going to have 1 mole of aluminum above, and the molar mass of aluminum is 26.98 grams per mole. So I'm going to put that down here. 26.98 grams of aluminum, all right? And then the next step is looking at the mole ratios of hydrogen to aluminum. And based on the balance equation here, there's a 3:2 mole ratio. I'm going to put 3 moles of hydrogen above, and down here I'm going to put 2 moles of aluminum, all right? So let's see what that gives. 1.5 divided by 26.98 times 3 divided by 2. Okay, is that right? Let me do this again. 1.5 divided by 26.98 times 3 divided by 2. Okay, so I got 0.0834 moles of hydrogen, all right? Now, the reason why I do that, and I probably should have stated this before, what we're trying to do is find the volume of hydrogen, right? Which would be equal to, based on the ideal gas equation, the number of moles of hydrogen times R times T divided by the pressure of hydrogen, all right? So we just calculated this. What we do need to get now is the pressure of hydrogen, because we already know what the temperature is, all right? So how do we get the pressure of hydrogen? Well, according to the question, the barometric pressure is 742 torr. And remember, we said from the previous slide, we said that the barometric pressure, P bar, that's going to be equal to the vapor pressure of water plus the pressure of the gas being collected, which in this case is hydrogen. So what we need to do is find the pressure of hydrogen so we can plug it into this equation. And that would be equal to the barometric pressure minus the vapor pressure of water, all right? Now, the barometric pressure is 742 torr, and the vapor pressure of water is not given. So we would have to, if I were to give you this question, I would have to provide that value to you. So what I'm going to do is do a quick Google search to find the vapor pressure of water at 22 degrees Celsius. And let's see what that gives. So according to this here, at 22 degrees Celsius, oh, that's not water. Oh, 19.827. I'm just going to round it off. Let me see here. I'm just going to round it off to, I'm going to round it off to 19.8. But I would have to provide that value to you, right? So I'm going to put here 19.8 torr, all right? So basically, 742 minus 19.8. So according to my calculation, this works out to be equal to 722 torr, all right? So that's the pressure that we're going to put here in this equation. So let me, whoops, okay. So I'm going to need some more space here. So let me do some ratio. I take it that you have written down all this, right? Okay, so let me erase some of this here. Okay, so basically, to find the volume of the hydrogen, that will be equal to the number of moles which I just erased. What was it? Can somebody remind me? I just erased it. .0834. Yeah, that sounds right. Okay, so that's the moles times R, which is 0.0821 liters atmospheres over mole Kelvin, times the temperature, 22 degrees, plus 273, that gives you what? 295 Kelvin. And then divide all of that by what we just calculated here, which is 722 torr. However, we have to do some conversion here because we have torr here, we have atmospheres here. So what I would do is convert that to atmospheres. 1 atmosphere, if you look it up in the document that I've posted in Canvas, 1 atmosphere is equal to 760 torr, all right? So in terms of units cancellation, the moles will cancel out, the kelvins will cancel out, the torrs will cancel out, the atmospheres will cancel out. So your final answer would be in liters. So let's see what that gives. 0.0834 times 0.0821 times 295 divided by 722 divided by 760. Okay, so according to my calculations, rounded off to 3 sig figs, according to my calculation, this works out to be equal to 2.13 liters. And that's basically how that problem is done. So this is again another typical gas stoichiometric type problem. All right. Okay, any questions about this? Any questions? Any questions? Okay, let's see here. Let me go back to, are you finished with this, writing this out? All right, so let me go to the PowerPoint here and see what's next. Okay, so based on what we have just covered, I don't want to touch this yet until you do some problems on what we have covered. So based on what we have just covered, let me go back here. And let me go here. Okay, so based on what we have covered, you should now be able to do questions 8, 9, 10, 11, 12. Okay, so we'll stop at 12 for now, all right? Okay, so what I want you to do now is start off looking at question number, where did I say? 8. Yes, question 8, all right? So I want you to try that now, and I'm quite sure you're going to encounter some challenges. So feel free to ask your questions while you're trying this. This question is talking about a mixture of gases, and it gives you the amounts in grams. It gives you the temperature, and it gives you the volume of the container, which is 1.00 liters. And the question is asking for you to calculate the partial pressure of each component. All right, let me have you try it first, and then we can discuss it if you have any problems. Oh, somebody has actually, oh, Mr. Donnelly, you're here. Just noticed that you have joined us. Make sure I have your attendance down. Let me see if I can give you a little help or hint or whatever. The question is asking for you to calculate the partial pressure of each component, right? So what equation comes to mind when it comes to calculating the partial pressure of each gas in the mixture? What equation comes to mind? Okay, so let me write that down. P for each gas would be equal to nRT divided by V, right? So the question gives us the temperature, right? And the question gives us the volume, and we all know what R is, right? So basically it comes down to the number of moles. We need to know the number of moles of each gas, right? And we all know how to do that. Now, let me just say that what we could do is, since we know that the number of moles is equal to the mass in grams divided by the molar mass, we can rewrite this equation as mRT over uppercase MV, right? This is the mass in grams, right? And this here is the molar mass. You see what I'm saying? So basically, this is the equation that you could use to calculate the partial pressure of each of these gases, because in each case, you're given the mass in grams, and in each case, you can divide or you can determine the molar mass and you just plug those numbers into that equation, and you can get the pressure of each gas. Yes, sir. Oh, don't wanna, okay. Well, okay, let's think about number 9 now. Hold on, let me do this first. Okay, now in the case of number 9, it says here that you have container A and it gives you the volume and it gives you the pressure of the gas in it. Container B, same thing. They give you volume and pressure in container C, all right? And it says if all the gases are put into container D and it gives you the volume, the question is, what is the pressure in container D? Well, what I would have to do is find the pressure of each gas in container D, right? So you can't just add them up. What you'd have to do is look at, okay, for container, let's focus on container A. This is the initial volume, right, of the gas in container A, and this is the initial pressure, right? So the final volume is the volume of container D, right? And the question is asking for the pressure of the gas in container D, right? Now remember, I'm just focusing on A, so I'm just going to say for A, P2 would be equal to P1 V1 over V2, right? Which is Boyle's law, right? And then you put the numbers in. So for P1, that's 3.24 atmospheres times V1, which is 1.23 dm cubed, divided by V2, which is the final volume, which is 1.51 dm cubed, right? And then you work that out. So this would be for A. And then you'd have to do a similar calculation for B, right? Now, in the case of B, P1 would be 2.82, V1 would be 0.93, and V2 would be the same final volume. And then once you find out for B and for C, do the same calculation, you add them up, and that will give you the total pressure in container D. Yes, sir. Hmm? Okay, so R is basically is the same number, 0.0821. But before you do that, are you using this equation or this equation? Okay, if you're using this equation, then the N here would be the moles, right? The only way you get that is divide the 3 point, like in the case of nitrogen, you're going to divide the 3.5 by the molar mass. What you have here is a molar mass. Okay. You see what I'm saying? Okay. So what you have to do is divide the 3.50 by this, and that goes here. Okay. The R is going to be 0. Let me borrow your stylus. The R is going to be, let me write it here. R is equal to 0.0821 liters atmospheres over mole Kelvin. All right. You can find that in the tables. All right. But that's it. Okay, yeah, it looks right. The only thing is that this here, it's a minor thing, because you have two sig figs here, this should be rounded off to 1.7.
Okay.
And then when you add these together, this will be rounded off, I think, to 1 decimal place. Make sure you show the work where you add this, this, and this. All right. But apart from that, yeah, that looks all right. So oh, this is 0.8.
Yeah.
Okay. I thought it was 0.1 for a minute. Okay, so that goes here. Okay, so that looks correct. And then for this one. Okay, now for this one, so far so good. But the question is asking for the moles of one. Oh, okay.
It's just that number seemed really big. So I didn't know if I was doing it right.
Well, it looks right. The only thing is that because you have two sig figs here, you should round this out to 93. But apart from that, it looks right so far. Okay, folks, we're going to end it for today. So continue working on those problems. If you have any questions, please feel free to contact me, and see you guys next, well, Thursday. See you guys. No, wait a minute. There's no class on Thursday. See you guys next Tuesday. I completely forgot. Remind me of your name, because I was about to search for that thing that you were asking me about. And I could,
Jack
what's the last name?
Levigood.
Levingood. Okay, let me make sure I record it so that I can let me see here, Levingood. And I'm looking for what exactly again?
It was one of the signs. It was the non.
Levingood.
It was this one, I'm pretty sure.
Nomenclature. Oh, that's a lab.
Yeah.
Okay, my bad. Okay, so. It's a pencil. Levingood. Nomenclature. Okay, so I'll definitely search for that. All right, that I didn't remember your name, so that's why.
So do we have live today?
Yes, the alum one. Mm. Yes, sir.
Or do I just go?
You can come to me. I've been told that there's tutoring offered I do Ocala campus, but I don't remember. I know it's in the library building. I don't remember what room it is, but let me see something here.
I'm like struggling on that chapter.
Oh, really? Well, like I said, you can see me.
Yeah.
Um,
Are you always at like this office?
well, it depends on the day. So basically for this semester, I'm here in my office on Thursdays. Let me show you. On Thursdays from 8 to 11 and then 2 to 5. And then let me see here. I'm online on Fridays from 2 to 6. And I'm at the Ocala office from 2 to 5 on Mondays. But all those times I'm on Skype anyway. So if you can't make it in person, just call me up on Skype and we can talk.
Okay, I'll definitely ask.
Mhm. Yeah, it's somewhere in the library. I don't remember where, to be perfectly honest. I'm trying to figure out who you should ask concerning that. Okay, hold on. Tutoring, okay, tutoring. Apparently, let me see here. Okay, so basically, oh, they say Citrus. I didn't know that they offered it here, but yeah, this is the library building. So if you call extension 1246, I guess they can probably make arrangements.
Okay.
Somebody did tell me that they have a student over there who helps other students in chemistry, so. But, like I said, you can also contact me.
I'll probably.
All right. Yes, sir.
Thank you.
Mhm.